Alright class, Bismillah ar-Rahman ar-Rahim, Assalamu alaikum, and welcome to the first lecture of the third week, and we'll start right away from the main topic, that is cylindrical coordinate system. In the last classes we had discussed extensively about rectangular coordinate system, and by the way, don't be intimidated by these figures. When we'll get into it, things will be very simple for you to understand. So we will follow the exact order that we did when we were discussing Cartesian coordinate system, and as we all know that a coordinate system is always defined to locate a point or define directions of one point with respect to another point. So let's say we have got this right-handed coordinate system x, y, and z, and we want to locate this point P, whose coordinates are x1, y1, and z1, and obviously in rectangular or Cartesian coordinate system. So these coordinates are nothing but the coordinates which are telling you that if you draw perpendicular from this point on the xy plane or z equals 0 plane, the height of this line is nothing but z1. And now if you have got this point, the new point, which is the intersection of this vertical line and the xy plane or z equals 0 plane, from this point, if you drop a perpendicular on x-axis, what you'll get is y1, the y coordinate, and if you drop a perpendicular on y-axis, you will get x1. So this is perpendicular, and this is also perpendicular. This is perpendicular to what? This is perpendicular to this line is perpendicular to xy plane. Okay, so this is a point. So if you want to reach this point from origin, we would say move in the direction of x, how many units? X1 units. Move in the direction of y, how many units? Y1 units. Move in the direction of z, how many units? Z1 units, and you will reach this point. So we write this because it is starting from origin and terminating at an arbitrary point P. We say that this is x1 ax plus y1 ay plus z1 az. This is nothing but a position vector. So if I draw a position vector from this point to point P, this is RP. Okay, the bar on the top, it is mandatory to write for you all because it shows that this RP is not a variable, rather it is a vector. So if I draw the projection of this whole vector on the xy plane, what I will get this line. Okay, I'll get this line. Since this line is on xy plane, this vertical line is perpendicular to this plane. So this is something you all know. Okay, now in cylindrical coordinate system, we have to define a new coordinate system. To reach that point, we would need one additional information. Okay, so actually when we were using Cartesian coordinate system, which is the most general form, I just gave you one point and said locate it. So you just established XYZ axis, you established origin, and you gave the address of this point P. But now, what if I tell you that this point lies on a cylinder? This is an additional information which I'm giving you, meaning that I'm saying that here is a cylinder in three-dimensional space, and on that cylinder there is a point P. Now locate it. So what you can do, you can establish XYZ in any way possible, but obviously what you do, you will establish z here, y here, x here, and give the location of this point in this form. But we know that an additional information has been given to us this time, that this point lies on a cylindrical surface. Now a symmetry exists. So you know this shape is symmetrical about something. About what? This shape is symmetric about its central axis, you know, okay? Just like a circle is symmetric about its center, okay? Symmetric means every point on the circumference is a distance r, radius distance away. This r is, by the way, radius distance away from the origin. Similarly, a cylinder is some distance, let me call this radius rho, some rho distance. Every point is some rho distance away from the central axis. So this is how a cylinder is defined. Cylinder is defined by two things, just like a circle is defined by two things, a center and its radius. Similarly, a cylinder is nothing but a three-dimensional version of a circle. If you just introduce height in it, you will get this thing, you will get a cylinder. So cylinder has got two things which you should take care of, which should be defined, otherwise that cylinder cannot be defined, and that is a central axis and the radius of the cylinder, okay? All right, so it means that the radius of the cylinder is always measured from the central axis, okay? So if I want to measure a point, a radius of this cylinder at this point, from this point, so what I will do, I will drop a perpendicular on the central axis, and then the length of this perpendicular will be the radius of the cylinder. If I am at this point and I want to measure the radius of the cylinder, I must drop a perpendicular on the central axis and then measure the length of this perpendicular, and in that case now that length of that perpendicular is the radius. Let's say I am at this point, so I want to find the radius, so I have to drop perpendicular with respect to this radius, okay, the central line, okay, perpendicular on the central line. If I am here, drop perpendicular on the central line. So now we have got the radius here, okay? So this is a must thing. Okay, so if an additional information is given to you that this point is located on the surface of a cylinder, in the case of Cartesian coordinate system, it was not given to you, nothing was known about you about the point, but now this additional information is known, that it is on the surface of the cylinder. So what we can do to locate it, the intelligent way to do it is to take this central axis and make it z-axis, all right? Make it z-axis, and then once since we are using right-handed coordinate system, if the thumb is the z-axis, index finger is x-axis, and middle finger is y-axis. So it means that this is x-axis, this is y-axis. So the right-handed coordinate system forces us to establish x, y, z in this fashion. If we have decided to take the central axis of the cylinder as the z-axis, then we have no choice other than use this as x and use that as y. So now how to reach that? Okay, before that, just to support your visualizations, just to aid you with your visualization, I have a question to ask. If I've got a cylinder, and if I cut it through a plane, what I will get at the intersection? I'll get a circle. If I dip this cylinder, hollow cylinder, in the ink pad and just press it here, what I'll get a circle, obviously. So always remember the intersection of a cylinder through a perpendicular plane always gives us a circle. So we know that this is an infinite cylinder, and this cylinder must be, you know, intersecting this xy plane, or in other words z equals 0 plane, because z equals 0 plane is nothing but a horizontal plane intersecting a plane. Z equals 0 plane is nothing but a plane which is parallel to both x and y axis, meaning it is an xy plane, and intersecting z axis at 0, and also obviously because it is parallel to x and y axis, that z equals 0 plane is also perpendicular to z axis. So z equals 0 plane is nothing but xy plane. So if I want to know the intersection of z equals 0 plane and this whole cylinder, what I'll get? I will get a circle whose radius is the same, rho. Okay, I can just remove this now, and whose radius is rho, and this circle is lying on z equals 0 plane, or in other words xy plane. Okay, now to reach this point, what I can do, I can drop a perpendicular from this point on to this circumference, that is exactly z equals 0 plane, exactly what we did in Cartesian coordinate system. So this height will give me the z coordinates. Let's say this height is z1. This is exactly how we defined z axis in Cartesian coordinate system. Now once I am here, okay, this is the point. Okay, now I want to locate, keep this point in mind. Okay, I want to locate this point with respect to origin. Now I cannot use xyz, I have to use some other coordinates. We are defining those coordinates. All right, so I would say move in the direction of a reference axis. Previously we said move in the direction of x1 units, but now there is nothing as x, y and z. So we are saying that we are moving in the direction of a reference axis, and we are calling that reference axis as x-axis. So move in the direction of reference axis. How many units? So much that you reach at the circumference of this circle. So in other words, move from the center in the direction of a reference axis so much that you reach the surface of the cylinder. Now remember that this line is along z equals 0 line. This line is along z equals 0 line. Okay. Now once you have reached the surface of the cylinder, move along. Now keep rho constant, just like we did in rectangular coordinate system. Move in the direction of x, then move in the direction of y. When we were moving in the direction of y, x was constant and z was constant. When we were moving in the direction of z, y was constant and x was constant. So this is the beauty. This is the beauty of this is the way actually to define coordinates, that if you are moving in one direction, the other two coordinates should not be changed. Otherwise that coordinate or that direction will not be defining any independent coordinate. Okay, so if you are moving in this direction, nothing is changing, you are just moving in the direction of rho. Now once you reach the surface of the cylinder, now move along the surface, move along the z equals 0 plane and reach that point which is directly beneath that point which we want to reach. Once you have reached this point, now join this point by that point. Okay, it means that now the coordinate which will give you the point which is directly beneath the target point, that coordinate is an angle, and we represent that by phi. And then finally move in the direction of z. Similarly, in the same way that we did in Cartesian coordinate system, move in the direction of z. How many units? Z1 units. So let's say this radius is rho 1, this angle is phi 1. So now we would say that we have reached to the point P whose coordinates are rho 1, phi 1 and z1. It means that now we have got a new set of coordinates: radius, angle and height. with respect to z equals 0 plane, height with respect to z equals 0 plane. So generally I can write that in cylindrical coordinate system, the coordinates are radius, angle and height with respect to z axis. That's all. So it means that we should expect a different position vector in case of cylindrical coordinate system. Now we have defined how to reach here. Okay, now let's discuss the foremost thing in defining or explaining or creating or specifying a new coordinate system. Number one thing was fundamental surfaces. So how did we define fundamental surfaces? Keep one coordinate. This is first fundamental surface. Phi equals constant as second fundamental surface. Z equals constant as third fundamental surface. All right. So rho is equals to constant is the collection of all the points whose distance, because remember that this rho is nothing but perpendicular distance of any point with respect to z axis. It means that collection of all points whose distance with respect to z axis is constant, is rho equals to constant. In other words, rho is equals to constant is nothing but a cylinder of infinite height but constant radius. Okay, so there we go. Diagram number Aleph on the right hand side. This diagram. We have got x-axis here, we have got y-axis here, we have got z-axis here, and this cylinder whose radius is rho, whether measured from here or here, I am not sure whether you are able to see this, but this is written rho. So this cylinder is nothing but rho equals to constant fundamental surface. This, remember that this height is infinite. All right, and this in figure number B, we have got I've just shown you the intersection of this rho equals to constant surface with z equals 0 plane, just the one which I drawn right there. Okay, so this circle is nothing but the circle which I drawn on z equals to 0 plane. Again, this is the same, the base of this cylinder, maybe at infinity, and the radius, if you want to find the radius from this point, you just have to take the perpendicular distance. Always remember that. It means that this line, this radial line, always lie on the horizontal plane, whether it is z equals to 0 plane or z equals to, let's say, z1 plane, or z equals to z2 plane, or z equals to -3 plane, something like this. So this rho radius is always on the horizontal plane. Remember that. All right, this so this is a cylinder. I'm just writing cylinder of infinite height along z axis but of constant radius, and that constant radius is given by this constant. So the second fundamental surface is phi equals to constant. Phi equals to constant should be collection of all the points which make a constant angle with respect to the reference axis, and in our definition that reference axis is x-axis. So let's see diagram number P. Okay, so this is x-axis, y-axis and z-axis. So you can see this plane. Okay, this plane, this dotted line lies on that plane. This plane can be thought of as a door. एक दरवाजे के तौर पे आप तस्वुर कर सकते हैं इसको, which is fixed along the z-axis but whose handle is somewhere here and you can open and close it. Alright, एक ऐसा दरवाजा जो z-axis पे fixed है और आप यहाँ से उसको खुल बंद कर सकते हैं, घुमा सकते हैं. You can revolve this door around z-axis. Alright, so if I want to find the angle of this plane with respect to our reference axis, which is x-axis, In that case, what we'll have to do, we'll have to draw a line on this on this plane, on this phi equals constant plane. Okay, if and this dotted line is also on z equals 0 plane. Okay, this line is not only on phi, this door, this line is not only on this door, but this line is also on z equals 0 plane. Why? Because this x-axis is also on z equals to 0 plane. So the right way to measure angle of a plane with respect to an axis, axis x, is to, you know, measure it on the same plane. If x-axis is on z equals 0 plane, then you should measure this angle on any line on this radial on this phi equals constant surface which is on z equals 0 plane. So just to elaborate this idea, I've just given this another diagram. So this is the radial plane. All right, and if I want to find, this is the same thing, the same angle, and actually if I want to find the angle, if I'm standing here, I want to find the angle of this plane. I'm standing right here on at this point on the door, on that phi equals constant plane. I'm standing here and I want to find the angle with respect to the reference axis, which is x-axis. So the right way is to draw, is to slide this x-axis at the same height and then measure the angle between this line and that line. Okay, so this line should be on z equals z1 plane and this axis should be on the same plane. Okay, if you try to measure the angle with respect to the x-axis which is on z equals 0 plane and try to measure it like this will give you a wrong value. This is not the right way to measure the you know, azimuthal angle, which we call it normally, azimuthal angle, the angle which lies on the horizontal plane. This is not the right way to measure it. The right way to measure it at any arbitrary point is to shift the reference axis, which in our case is x-axis, shift the x-axis at the same level, at the same z plane, and then measure the angle on the horizontal axis. So the take home message is phi always lies in z equals constant plane. So this is written, I'm not sure whether you are able to see it, phi always in z equals constant plane, that is the horizontal plane. So there are two things now. Rho, the radius, is always measured in horizontal plane, and the phi also lies on the horizontal plane. Two things. Okay, so we have got a, you know, a radial plane. We call it radial plane. Why? It will be cleared in within a moment, inshallah. So the third is z equals constant plane is the same as the Cartesian coordinate system, figure A. Okay, so horizontal plane. So this is horizontal plane, and this point is this constant value, whatever the constant value may be. Now from this figure, next figure, say this next figure, say what I'm trying to do is I'm trying to plot two fundamental surfaces at a time. So just to be complete, for the sake of completion, this will be horizontal plane. Okay, all right. So so now from this figure, what I'm trying to do, I'm trying to mix this. I'm trying to draw two fundamental planes at this on the same set of axes, meaning I'm trying to combine bay and pay here. Okay, in this figure say, and I've taken arbitrary values. Let's say radius of the cylinder is 3 and angle of the radial plane, this plane, radial plane, with respect to x-axis is, let's say, 60 degrees. All right, so this is the cylinder and this is the radial plane. You can pause here and see, okay, and the intersection of the two, this cylinder and this radial plane, the intersection of the two will give you this yellow or red line, whatever you are seeing, I'm not sure, but this, for me, it is yellow, this vertical yellow line. So it is something like this. This is the cylinder, this is the cylinder, if and this scale is nothing but, you know, the radial plane. So if I cut it through, okay, if I cut it through, what I will get at the intersection of this cylinder and this radial plane, I will get a straight line like this. I'll get a straight line like this, okay. So now in figure G, what I have done, I have just shown you the resultant of two intersections. So how a line is being defined here, we are defining a line in terms of the fundamental shape, that in cylindrical coordinate system, vertical lines are nothing but intersection of rho equals to constant and rho equals to constant cylinders and phi equals to constant radial planes, okay. So vertical lines are defined which are not fundamental shape, so they must be defined in the form of in terms of fundamental shapes, and you will say that vertical lines in a cylindrical coordinate system is nothing but intersection of a cylinder and a radial plane. So this figure number G is showing you this vertical line whose perpendicular distance, okay, this line is showing the perpendicular distance, and these, you know, triangle kind of thing, they are just showing that this line is making 90 degrees with respect to this yellow line, and this line is also obviously making 90 degrees with respect to this z-axis, because this yellow line and z-axis both are parallel to each other. So the distance is 3 because radius of the cylinder was 3. Now in figure number, you know, J, what we are doing, we are trying to show the intersection of rho equals to constant and z equals to constant. Now this combination, earlier it was this combination, now this combination. And this figure you can see that this is the horizontal z equals constant, and I have taken any value z equals to 2. It means that this point should be z equals to 2, and the radius of the cylinder is the same. So as we already have discovered that the intersection of a horizontal axis, a horizontal plane and the cylinder, if they intersect perpendicular to each other, not meaning this cylinder is not making any angle with respect to horizontal axis other than 90 degree, in that case we'll get a circle. In that case we will get a circle. क्योंकि हम 3-dimensional व्यू देख रहे हैं इसलिए आपको ये सर्कल थोड़ा elliptical नजर आ रहा है. If you will see it from the top, you will see what you will see is a circle. This is a cylinder, perfect cylinder. But if you see it from here, this cylinder can be seen as an elliptical surface. Okay, you will see an elliptical surface, although it is a perfect circle. Okay, so remember that whenever you will see a circle, whenever you will see a cylinder from, you know, a certain angle other than the top view, you will see an elliptical, एक चपटा सा cylinder आपको circle नजर आएगा, you know, ellipse sort of thing you'll see. All right, so if I remove these surfaces and just show you the intersection, what I'll have rho equals to 3 and z equals to 2. This circle, I've just removed these surfaces. Remember that whenever we talk about points or lines in 3-dimensional space, we don't show the constituent fundamental surfaces. We just show the intersection of the two fundamental surfaces. If we are talking about a point, then we just show the point. All right, we never show the constituent surfaces. All right, so you should remember that a circle is always defined in a cylindrical coordinate system by the intersection of a horizontal plane z equals constant and the cylinder, both intersecting each other at perfect 90 degrees. Now the third combination would be intersection of this phi equals to constant and this z equals to constant plane, which is given in figure number K. All right, so you can see that this is the horizontal plane. All right, this plane must be intersecting. Should I draw it here? This plane must be intersecting this z-axis on z equals to 2. All right, z equals to 2. Oopsie. Okay. And we know that this is the horizontal plane and this radial plane. Wherever they will intersect, they will form this blue solid line. Okay, this line is on z equals 0 plane and also on phi equals 60 degrees radial plane. That's why it is the combination of the two, that intersection of the two. All right, so now again, removing the fundamental surfaces, what will get a straight line. So in order to get a horizontal line, always remember, in a cylindrical coordinate system, you need to have intersection of two fundamental planes, that is phi equals to constant and z equals to constant. Now figure number dal. Okay, combination of all the three, rho equals to constant, phi is equals to constant and z equals to constant, drawn on the same plane. You can see cylinder of constant radius, rho equals 3, radial plane of constant angle, phi equals 60, and the horizontal plane z equals to 2. So again, at the intersection of this cylinder and this radial plane, we have got a line. Remember that we have got a line, this yellow line. And at the intersection of this cylinder and horizontal plane, we have got this green circle. Okay, and intersection of this radial line and horizontal plane, we have got this blue line. Now removing all these three, the fundamental surfaces, what we have got, the fundamental, the not fundamental but the two-dimensional entities, a line, vertical line, a horizontal line, and a circle. All right, and the intersection, which is given by this dot, this intersection is the point which has got the coordinates of 3, 60 and 2. 3, 60 and 2. So you can say that a point in cylindrical coordinate system is formed by the intersection of these fundamental surfaces, and the fundamental surfaces are shown to you. What I have done in the next diagram, in next figure R, this figure ray is showing us the same thing, but I have reduced the thickness of the fundamental surfaces just to emphasize on the lines which are being formed. And again, this is the point which you can see over here, which is being formed by the intersection of these three fundamental surfaces. And what I have done in this figure ray, that this I'm showing this diagram Okay, I'm showing you in figure A, I'm showing you the top view of figure A. If you see it from the top, you will get this. You will see the cylinder as the circle. You will see this circle, this green circle, you will see it as a perfect circle. Okay, and this line you will see as the line making some angle phi with respect to x-axis. All right, and this plane, horizontal plane, is something what you will see like this. Okay, so this is all right. At this, there is some mistake here. This is not phi equals constant. This is z equals to constant surface. Sorry, my bad. Okay, so this is the angle which is making. So now, why do we call this radial plane? Because if you see that this plane from the top, you can see that this plane will be will be a line. अगर आप प्लेन को ऊपर से देखें आपको लाइन नजर आएगा. This is the plane. If you see from here, you will see a line. Okay, from here you will see a line. So this line is nothing but the radius, the radial line of this circle in 2 dimensions. So in 3 dimensions, you can see that this plane is nothing but the radial plane of the cylinder, which starts from the central axis and goes through the circumference, which starts from origin and goes through the circumference of the circle. So what does it mean? It means that this line is also perpendicular to the circle. This is a property of the radial line. So this plane is also perpendicular to the cylinder. That's why it is called a radial plane. All right. So I would like you all to give it a pause here and try to see all these 15 diagrams. Okay, and then we'll talk about the next big thing, which is the primitive unit vectors. All right, primitive unit vectors. So give it a thought, watch all these 15 diagrams and try to remember these things. All right. So now you know that you should have known by now that this green circle, which is the intersection of this horizontal plane and cylinder, and this blue line, which is the intersection of 2 planes, one radial plane and the horizontal plane, both of them lie on the horizontal plane. And we have already talked about this radial plane and this cylinder intersect. Wherever they intersect, they form vertical line. So this vertical line should be perpendicular to horizontal plane. That's the reason why we are seeing this yellow line as a yellow dot in 2 dimensions if we are looking from the top. All right, so it means that z-axis is coming out of the board. This yellow line is coming out of the board now. To define primitive unit vectors, we all know that since we have got 3 fundamental surfaces, we should have 3 unit vectors, primitive unit vectors. All right, there we go, 3 unit vectors. And remember the properties of these 3 unit vectors. All of them have got unit magnitude, granted, no discussion about that. 2 major properties, that a rho is perpendicular to rho equals to constant, a phi is perpendicular to phi equals constant, a z is perpendicular to z equals constant. Number 1. Number 2, a rho is pointing in the direction of increasing values of rho, a phi in the increasing value of phi equals to constant, a z in the direction of increasing values of z. Sorry, this a phi should be pointing in the direction of increasing values of phi. All right, so let's try to draw it here. So if I'm at this yellow point here, if I want to go at the point, and remember that in the case of Cartesian coordinate system, when we were moving in the direction of ax, the coordinates y and z were not changing. All right, this is also the property of the primitive unit vector. Otherwise that unit vector is not primitive, that if you move in that direction more than one coordinate changes, it means that that direction is not a primitive unit vector. In the case of Cartesian, remember, you were moving in the direction of x, y, z was constant. You were moving in the direction of y, x, y, x, z constant. You are moving in the direction of z, x, y constant. So if I am here at this point P, which is formed by the intersection of these three planes, and I want to find the direction of rho, arrow, I mean, so I should move from that point, I should move in a direction which is perpendicular to rho equals to constant surface, meaning this is the circle, and we know that the radial line, I am now using the blue marker, we know that the radial line is perpendicular to the green, this radial line is perpendicular to this green circle. It means that if I move in this direction will be perpendicular to the circle. Okay, this direction is also perpendicular to the circle, but this direction will bring me closer to the center, which is nothing but this central line, meaning if I'm getting closer to the z-axis, the values of rho will be decreased. So this direction is the correct direction for a rho. Okay, and now let's talk about a phi. A phi, if I am moving in the direction, if I'm at this point, and we know that this blue line is what? This blue line is this blue line is phi equals to constant line. So if I want to draw this a phi, that should be perpendicular to this line in this direction or this direction. Remember that this blue line is the phi equals to constant line. Okay, in fact I should have used green color for this. I should have used green for this. That would be much better, but never mind. If I am moving in this direction, that is tangent to the circle because it is perpendicular to this radial line, then this direction is what? This direction is a phi, because this direction is perpendicular to this phi equals to constant line, and it is pointing in the direction. If I move in that direction, this angle with respect to x-axis will increase. Okay, so maybe I can do it here in 3 dimensions. In 3 dimensions, if I'm at this point and I want to move in the direction of increasing values of rho, also that rho should be, that direction should be perpendicular to rho equals to constant. It means that I should move in along this direction, Okay, I'm drawing it with green color. I hope you would be able to see it in green. If not, I'm sorry. This is green and this is a rho. So this arrow, since it is along this blue line, this arrow is lying on the horizontal plane. And this a phi in 3 dimensions, a phi should be a unit vector which is perpendicular to phi equals constant radial plane, and it should be pointing in the direction of increasing values of phi. Remember that this radial line is always perpendicular to circumference of the circle, and anything which is perpendicular to this radial line will be tangent to the circle. All right, so if this line is along the radial plane, so radial plane is always perpendicular to the cylindrical surface, then anything perpendicular to this radial plane will be tangent to the cylindrical surface. Okay, but tangent is not important since we are trying to define a phi. Since we are trying to define a phi, that a phi should be perpendicular to this radial plane, and it is. You can see it from this two-dimensional diagram. This horizontal line is phi equals to constant diagram. Phi equals to constant line in three-dimensional. This is phi equals to constant plane, and this a phi is perpendicular to that plane. So it means that one is in the direction of radial line, the other is perpendicular to that. It means that there is a 90 degrees difference between a rho and a phi. A rho and a phi. A rho is pointing in that direction, a phi is pointing in that direction. Both have got 90 degree out of phase. It is clearly shown and clearly observable in this two-dimensional diagram today. Okay, and since z equals constant plane is the horizontal plane, and it has been defined in the same fashion as it was defined in the Cartesian coordinate system, so remember that AZ is coming out of the board, or in this case, if we are at this point, it will be in this direction. This is AZ. So a rho in this direction, a phi in this direction, both are 90 degrees out of phase. Z axis is going out of the plane. So it means that at the point of intersection, all the three radial planes, all the three unit vectors are perpendicular to each other, means that all the fundamental surfaces are perpendicular to each other at the point of intersection. Remember that, just like in the case of Cartesian coordinate system. So one more thing, in the case of Cartesian coordinate system, we had the unit vectors fixed in one direction, all right, but in here in cylindrical coordinate system and also in spherical coordinate system, the direction of unit vectors changes with respect to the point. Let's say if we were standing at this point, okay, and now we would want to find a rho. In that case, now let me use the correct marker here. So moving in the from here, move in the direction which is perpendicular to rho equals to constant circle, that is move in this direction. We could have moved in that direction also, but this direction will bring us closer to z axis, meaning it will reduce the values of rho. So that is not the case. That should not be the case as per the properties of unit vectors. So this is the direction of a rho. Now a phi, this black line, radial line, is nothing but the line, the phi is equals to constant line. So if I want to know a phi, that should be a perpendicular to this line, and that perpendicular could go that way or it could go this way, but this way is the way which is bringing me away of this radial axis, meaning in this direction the values of the angle will increase. If I move in this direction, the value of the angle will increase, and z remains the same. So now you can see that the direction of rho and phi changes with respect to the point. Wherever you are standing, unit vector will be defined with respect to that point. Luckily, in Cartesian coordinate system, this was not the case. Wherever you stand in the three-dimensional Cartesian coordinate system, the unit vectors always point in one direction. But now remember, in cylindrical coordinate system and also in this next topic, spherical coordinate system, the direction always changes. The direction of rho and phi may change, not always, may change depending on the point at which you are standing. For instance, if I am standing anywhere on this vertical line, the direction of rho will not change. Why? Think yourself why. So alright, okay, if I'm moving along this line, the direction of phi will not change. Why? Think it for yourself why. If I move along this line, okay. All right, so that's it for today. The only topic which is now left is differential volume, differential surfaces, and differential length, and then the vector components and the position vector in case of the cylindrical coordinate system. Probably will take the next half class in discussing that, and then inshallah we'll start with the spherical coordinate system, and this whole week will take up the definition of mathematics. Okay, for now, assalamu alaikum.